Hi, everybody, and welcome to our Intro to Statistical Concepts for Social Sciences webinar. These are just going to be the frequently asked questions that we get from students, typically in the undergraduate Intro to Statistics classes. My name is Alexis Mosstaller. This is Elizabeth Mathers, and we're just going to go ahead and get started. So, we are going to start right here. This is an image of just your basic histogram. I just kind of wanted to cover the different parts of the histogram because it can provide a really helpful visual for kind of understanding what's going on when we're doing statistics. So this is also known as a frequency distribution. The data that I have put in here is just test scores. So students in a class took a test, just got their average scores. As you can see, most students were kind of between the 75 to 84 range, which is like a C to a B. It was pretty average. There's some students that did better, some students that did worse. And you'll notice as you get farther and farther into these extremes, it gets smaller. So this is just a great way to visualize your data, to kind of see what's going on. You'll find that a normal distribution follows this kind of bell curve shape where it'll go up and then it'll go back down. And it's usually, if it's a normal distribution, it's pretty even on both sides. The mean is going to be this kind of big value right in the middle. That's where the majority of your people or your scores are going to fall. And the mean, for those of us who are just getting started with statistics, is the sum of all the values divided by the total. The standard deviation is then represented by these kind of chunks that go out on both sides. And that measures the amount of variation. So how spread out are your scores? Higher numbers in standard deviation are going to represent scores that are more spread out, whereas lower numbers are going to be kind of more centered around your mean. And then, like I said, each chunk here can represent one standard deviation. So if you have a score that's out here, that would be 2 standard deviations above the mean. And in case you need a little something to help you remember any of that, I don't know if you've seen the episode of SpongeBob where he's normal, but you can see he's got a little bit of that bell curve shape to him, and that is what a normal distribution should look like. We also wanted to go over the different types of variables, and this is going to be important as you go forward, running different statistical tests, being able to come up with your own research questions, things like that. So we're going to start up here at the top with nominal. Another word for nominal is name. So these are things that are just names. You can't really categorize them. There's not really an order to them. Things like gender, religion, Harry Potter houses, there's not really a hierarchical order to them. They're just names. Ordinal, however, you can rank. So there's not really an even number. They're not equally distributed between them. But if you have like a Likert scale, so you have, agree, disagree, strongly disagree, things like that. You have Olympic medals, you have gold, you have bronze, you have silver, or socioeconomic status. You can have, lower class, middle class, upper class. So you can understand that there's a ranking, but there's not like a specific numerical number that divides between these numbers or these values, sorry. Interval is where we do get those equal intervals. So you can have things like temperature, pH scale, credit score, numbers that, a higher number for temperature does represent a hotter temperature. However, with interval, there is no true zero. So a temperature of 0 does not mean that there's no temperature whatsoever. It just means that it's cold. If your credit score is 0, that doesn't mean that you don't have a credit score. It just means that it's really bad. So, and then finally, ratio is kind of the culmination of all of these different pieces. You have variables that have equal intervals, they mean something, and they have a true 0. So if you have height and somebody's height is 0, they don't have a height. There's nothing. Same for weight. If you have a weight that is 0, you just don't have a weight. Or age. If you're 0 months old, you have not been around for very long. Or number of children. If you don't have any children, then 0 really does mean you don't have any. So these are the different types of variables that you're going to see and you're going to need to become familiar with as you move forward in understanding kind of the general basics of statistics. So now we're going to get into hypothesis testing. I'll let you go ahead and take over.
It sounds good. All right, so hypothesis testing in statistics is the way that we draw conclusions using data gathered from experiments and surveys. So it allows us to draw inferences about a population using the information that we collect from a sample. All right. The process of hypothesis testing involves 2 types of hypotheses. The null hypothesis is the standard assumption, which predicts that the experiment has no effect, there's no relationship between variables, or that there is no influence of an intervention in an experiment. So in an experimental design, the null hypothesis states that the independent variable does not have any effect on the dependent variable. The alternative hypothesis, on the other hand, is what the experimenter hopes will be true. This is the opposite of the null hypothesis. So the alternative hypothesis predicts what will happen if the experiment actually works. I'm going to have the notation for these written as well. So for the null hypothesis, we write that as H naught. And you'll see that the sample mean of the first sample is equal to the mean of the second sample. So there's no difference between the groups. And then in the alternative hypothesis, H1, the mean of the first sample does not equal the mean of the second sample. So there is a difference between those groups. All right, so for example, we may have a situation where researchers are interested in studying whether a new blood pressure medication successfully reduces high blood pressure down to the normal range. In this example, our null hypothesis predicts that there's no difference from taking the medication or that there's not a significant change in blood pressure. And the alternative hypothesis predicts the opposite, that there is a significant change in blood pressure. And this is a non-directional or two-tailed alternative hypothesis because it doesn't specify what the change we might see is, just that there will be a difference somewhere. And a directional or one-tailed alternative hypothesis identifies what that change will be. So in this example, we would probably expect that the new medication is going to decrease the high blood pressure, or that we'll see a reduction. However, we could also predict the other direction, that the medication for some reason would increase blood pressure even further. Okay, so I also wanted to go over p-values a little bit. That's something that you're going to be hearing very often, and it becomes really important when figuring out if you are going to accept or reject the null hypothesis. So the p-value is essentially the probability that what you have observed could have just occurred by random chance. So for example, using Elizabeth's example, if you were to find that there was a difference in the blood pressure medication, what is the chance that you just found that accidentally, that it was a fluke? So in psychology, we use this p is less than 0.05 as the cutoff for deciding if our results are significant. If you run a survey and you find that your results have a p-value of less than 0.05, you can reject the null hypothesis, meaning that there's a less than 5% chance of finding your results due to random chance. Confidence intervals then are kind of involved with the p-values. It's the interval where you can expect to find the majority of your results. So if you think back to that histogram image that we had a little bit earlier, you have kind of your bell curve. The confidence interval is going to be a lower value and a higher value that kind of captures the majority of your data. It also, it contains 95% of your results, which is why it's called the 95% confidence interval. So down below, I have the formula for that, as you can see. And I've got a little cheat sheet in case you're not sure what all those letters mean. X is your sample mean,
You'll see that there's a plus or minus. That is because you need to find the positive and the negative value because you need both sides. But your Z is going to be the confidence level. Typically, it's that 0.95. The S is going to be the sample standard deviation, and then you'll divide that by the square root of your sample size. And that will give you your confidence interval, so you can know that the majority of your data is going to be within that range. Then we're going to progress a little bit further. So I hope you've been keeping up with what we've got so far. And we're going to start into Z-scores. And this is something that we in the SAM lab get a lot of questions about. So just to kind of give a basic definition, a Z-score kind of gives you an idea of how far away from the population mean a specific data point on your sample is. So if you just grabbed one person, their results, a Z-score can help you visualize and understand how their results compares to the overall population mean. It can range from -3 to +3. And again, it's in standard deviations. So if you'll remember back to our histogram from earlier, you have these different chunks that kind of spread out from the mean. Those are your standard deviations, and your Z-score is going to be measured in standard deviations. So for example, if you have a Z-score of 1.6, your data point is going to be 1.6 standard deviations above the population mean. Do keep track of if it is positive or negative. Positive is always going to be to the right of the mean or above the mean, and then negative is going to be to the left of the mean or below it. And just so that you're aware, there's a lot of lingo with Z-scores, but a Z-score and a Z-statistic are the same thing. So if you have an assignment that is using both of those terms interchangeably, do not worry, it is just looking for a Z-score.
All right, so as Alexis was saying, a Z-score shows you where a particular data point or score falls relative to the mean. So we can look at this on a distribution curve. A Z distribution is also called a standardized or standard normal distribution. And this is a special variation of a normal distribution or a bell-shaped curve where the mean has been set to equal 0 and the standard deviation is equal to 1. So when we're working with a Z distribution, there's an empirical rule that tells us that about 68% of all the scores within the data set will fall between plus or minus 1 standard deviation away from the mean. So looking at this bell curve over here, those are the values from 15%, 19.1%, 19.1% plus that 15%. That's going to be where 68% of the data falls. 95% of the data will fall within plus or minus 2 standard deviations, and then 99.7% of all the data will fall within plus or minus 3 standard deviations from the mean. And you can also see from this picture, like Alexis was saying, the Z-score is going to be the same thing as the number of standard deviations away from the mean that a particular data point is. So a Z-score of 0 is going to be 0 standard deviations away from the mean, so it's going to be the same thing as the mean. And a Z-score of 1 will be 1 standard deviation above the mean. And then these values can also be converted into percentiles or proportions. And then another thing about the Z distribution is that it's symmetrical. So anything that happens on the left side of the mean is going to be mirrored on the right side. So all of the data that falls below a standard deviation of, below a Z-score of -1 is going to be mirrored. So that's going to be the same percentage as the data points that fall above a standard deviation of +1, a Z-score of +1. So we've got an example of when might looking at a Z distribution be useful. So in this question, Agrabah is a vast desert city famed for its mysterious treasures as well as its scorching temperatures. A sample of 100 cities had an average summer temperature of 99 degrees Fahrenheit and a standard deviation of 8 degrees Fahrenheit. Agrabah's average summer temperature is 119 degrees Fahrenheit. And we're interested in looking at what percentile Agrabah falls in relative to the other cities in our sample. So the percentile indicates that the location of a score in a distribution, and it tells us what percentage of the population has a score that's lower than the one that we're interested in. So the first step for looking at this question would be to calculate a z-score for Agrabah. Here I've got the data points kind of copied in. So Agrabah, or X, is going to be the data point. That's 119 degrees Fahrenheit. Mu is the mean, which was 99 degrees Fahrenheit. And then that's all divided by the standard deviation in the denominator, which was 8 degrees Fahrenheit. So once we plug all of those values in, we have 119 minus 99, all divided by 8. And we end up with a z-score of 2.50. So after that, it's always helpful to sketch out a little z-distribution so you can visualize what you're working with. So here, again, we've got that laid out. The z-score of 0 corresponds to the mean of 99 degrees. And then a z-score of 1 corresponds to the mean plus 1 standard deviation, or 8 degrees. So 99 plus 7, or 99 plus 8 will be 107, and so on and so forth for the rest of the values written there. So if we're looking for that z-score of 2.5, we know it would fall somewhere between positive 2 and 3 on this curve, which will be about here. And then we were looking for the percentile that Agrabah is in, or how many cities is it hotter than. So we'll shade this whole region to the left of that line that we drew. So just visually looking at this, we can already tell that Agrabah is going to be hotter than most of the cities in our sample, since so much of that curve is shaded in. All right, so then moving forward, we have our z-score of 2.5, and we can pull up a z-table like the one over to the right here. And there's a few different variations of z-tables. This one, we can see it's shaded, over half of the distribution is shaded in. So we have that whole left half of it, plus a little further to the z-score, the positive z-score in this case. So to find that proportion or the percentile, we'll follow the column and the row to look at the z-score. So the first two values of the z-score were that 2.5, which I'll find in the column over here. And then we had a hundredths place of 0.00, so that'll be up here. And then to find that proportion, all we have to do is follow them into where they intersect, like this. And that'll give us a value of 0.9938, which is the proportion form. This question was asking about the percentile, so to find that, we'll multiply it by 100, and that gives us approximately the 99th percentile. So the information that this question has answered is Agrabah is hotter than 99% of the other cities that were in the sample. So definitely on the hotter side. All right, so there are quite a few different statistical tests available. So you might be wondering which is the right one to use in a certain question or under a certain set of circumstances. So we'll walk through this flow chart here. The test that you decide to use will depend both on the number of groups that you're comparing, as well as the information that you have available. Generally, when you have 2 groups to compare, you'll use a t-test. And when you have 3 or more groups, you'll use an ANOVA, or an analysis of variance. However, the specific type of t-test or ANOVA will change depending on the information that you've got. So starting off with the 2 group comparisons on the left side, one of our groups might be a sample and you'll have information about the population mean, or you might be working with 2 samples instead. So if you do know what the population mean is, and you know what the population standard error is, you would use a 1 sample z-test. If you know what the population mean is, but you don't know what the standard deviation or standard error for the population is, you'll use a 1 sample t-test. So the formulas for these are both essentially equivalent to each other, and it's just the type of standard error or standard deviation that changes between the 2 of them, whether you're working with the population version or the sample. Now, if we're comparing 2 samples to each other, you might have 2 entirely separate groups of individuals or participants, or you might have the same group of participants tested twice. For an example, separate groups of individuals, this might be comparing stress levels between men versus women, so 2 separate groups. And then an example of the same individuals tested twice. This might be comparing the stress level of a class before versus after taking an important test. Another common example for this would be like a pre-test, post-test situation. So you're testing the same people first here and then again later. So if you do have separate groups of participants, you would use an independent samples t-test. Then if you're testing the same participants twice, you'll use a paired samples t-test. And this same concept is also applied when we have 3 or more groups. So when all the groups are composed of different participants, we use a between subjects ANOVA. And then when we have the same group of participants tested repeatedly over time, you'll use a repeated measures or within subjects ANOVA. All right, so I think that covers about everything that we had laid out for today. I don't know if we had any.
Yeah, if you have any further questions, please feel free to make an appointment and meet with one of us at the SAM Lab. We're grateful for the time that you have spent today listening to our presentation, and we hope you have a great rest of your day.